Hi, my name is Tom Resh. I'm a specialist in the field of environmental testing, and I've created this video series in order to provide a better understanding of the theory and application behind various types of environmental tests. This current video series is on vibration testing. I hope you find these videos useful, and if you have any questions or comments, feel free to email me at tomvibetest@gmail.com. Thank you. This current video presentation is on vibration testing, terminology, and definitions. Again, my name is Tom Resh, and I'm an environmental test specialist. And if you have any questions or comments after this video presentation, feel free to email me at tomvibetest@gmail.com. Today's topics are abbreviations and definitions that you will encounter in the vibration test field. Some of the major abbreviations that you will encounter are G's, G's peak, G's RMS, millivolts per G, picocoulombs per G, decibels, and PSD, which stands for power spectral density. What does G represent? G is the unit of measurement for gravitational acceleration. Now, a lot of people confuse gravitational acceleration with gravitational force. This is not correct. Gravitational acceleration is a scalar quantity, while gravitational force is a vector quantity. Now, a scalar quantity is expressed only in magnitude. In this case, acceleration, the greater the magnitude, the greater the change in speed or change in velocity. We will go into more detail about velocity later on in this presentation. Gravitational force, which is a vector quantity, is expressed not only in magnitude, but also in direction. So gravitational force will not only tell you the magnitude of the change in speed of an object, but also the direction in which an object is traveling. Gravitational force is calculated by multiplying mass times gravitational acceleration, mass being the mass of the object, of course. Reiterated, G is calculated with mass to find gravitational force or weight, which is the force of the Earth on an object. Now, before we do an example, we are going to review some basic physics. Newton's second law of motion, to be precise, which states the net force is equal to mass times acceleration. We're going to use a variation of this formula. The negative weight force or force of the Earth on an object is equal to mass times acceleration. Now, why is this value negative? Well, think about it. Which direction is the force of the Earth applied to on an object? It is in the negative direction. If it was not a negative force, the object would float away into space, just like you and I would float away from the Earth into space. So it is a negative force. The weight force is a negative force. Now, we're going to perform some simple algebra and multiply both sides by -1. When we multiply both sides by -1, we get the weight force is equal to the negative quantity mass times acceleration. Now, we did this just to clean up the formula. Now that we have a formula, we are going to perform an example problem. What is the gravitational force of the Earth applied to a block with a mass of 10 kilograms? Now, since we are using a metric weight, we are going to use the metric unit of measurement for gravitational acceleration, which is estimated to be 9.81 meters per second squared. Now that we have the values we need to make our calculation, we will plug them into the formula we derived from Newton's second law of motion. The weight force is equal to the negative quantity, mass times acceleration. We will plug in 10 kilograms for our mass and 9.81 meters per second squared for our acceleration, which gives us the negative quantity 10 kilograms times 9.81 meters per second squared equals minus the negative 98.1 newtons. What's a newton? Newton is a metric unit of measurement for force. It is calculated by multiplying kilograms times meters per second squared, which we did. We had a kilogram unit of measurement, and we had meters per second squared for our acceleration unit of measurement, which gave us a Newton unit of measurement. So the force of the Earth applied to a block that weighs 10 kilograms is negative 98.1 newtons. Now, the original formula we derived our weight force formula from, force equals mass times acceleration, is a formula you will use quite frequently in the vibration test field. Let's go back to that formula. Now, why is this an important formula in the vibration test field? Well, shakers are rated in force. And in order to determine whether or not the force capacity of your shaker is capable of performing a test, you will need to multiply the sum of your masses times the acceleration of your test profile. What do I mean by sum of the masses? Well, in this case, we are not doing a simple object mass. We are doing a stack of multiple different objects with varying masses. You have an armature, which has its mass. You have a slip table if you're performing a horizontal test and its mass. You have the fixture for your test specimen and its mass. And you have your test object's mass, or your unit under test. You will then sum up those masses and multiply it with your given test profile's acceleration value. And this will determine whether or not your shaker has the force capacity to perform a given vibration test. Moving on, what does G's peak represent? G's peak represents the calculated peak acceleration, which is used typically in sine vibration testing. Now, we will define sine vibration later on in this presentation, but I wanted to give an example of what G's peak is used for. Now, we're going to define G's peak. You already know what G stands for. G stands for gravitational acceleration, which we just defined. Now we will go ahead and define peak graphically. I'm going to draw a vertical axis and a horizontal axis. And this is the first quadrant of a graph. And I'm going to define the vertical axis as y and the horizontal axis as x. I will now draw a crude sine wave. Now, peak the definition of peak is the peak or maximum positive value of a given data set. In this case, graphically, it's going to be the positive peak of your waveform. And it is calculated from the peak of your waveform to the horizontal axis. So let's go ahead and draw some hash marks on our vertical axis. And we will call them each 1G. Now, if we count these hash marks, given that each hash mark is 1G, we have 1, 2, 3, 4. So our G's peak for this given test is 4 G's peak. Now, moving on, what does GRMS represent? GRMS is the total acceleration content for a random vibration test. What does this mean? This means G's RMS is the area under the curve of your test profile. So underneath the spectral line, you would use integration to calculate your GRMS. Now, if the shape is simple enough, which it is for this given spectrum curve, you could use geometry. You could use areas of a triangle and areas of a rectangle to find your GRMS. It is just a simple area under the curve problem. Now, for more complex shapes, you would have to use integration. And some spectral shapes are so complex, it would take you weeks, even months to calculate it by hand. Luckily, or even calculator. Luckily, we have computers to do this for us very rapidly. So you will see this value or this term quite frequently, 6G's RMS, or you will see GRMS quite frequently in random vibration testing. So 6G RMS is the total acceleration content for this given random vibration test. Now, what does RMS stand for? RMS stands for root mean square, which is a statistical measure of magnitude for a quantity that varies, that a varying quantity. Now you'll appreciate why we use GRMS later on when we define random vibration, which has random quantities which vary and are not constant. Now, moving on, what is millivolts per G? Millivolts per G is the unit of measurement for voltage type accelerometers. It is the voltage type accelerometer's sensitivity. We will define what voltage mode accelerometers are in a later presentation, but for now I want to get you familiar with the different abbreviations for units of measurement that you will use in vibration testing. So once again, millivolts per G is the unit of measurement for voltage type accelerometer output. This is very important that you remember this quantity because you will use this quantity quite frequently in vibration testing when you are inputting your accelerometer sensitivity, because a lot of tests are performed using voltage type accelerometers. It's usually a standard. Now the other type of accelerometer is a charge type accelerometer, which uses a unit of measurement called picocoulombs per G. Once again, picocoulombs per gravitational unit is the unit of measurement for charge mode accelerometer output, which is also an accelerometer sensitivity. It's an accelerometer sensitivity for a charge type accelerometer. Now, depending on there are different types of tests and different instances when you would need to use a picocoulomb per G charge mode accelerometer or a voltage mode accelerometer which uses millivolts per G. We will discuss this in a later presentation. And once again, I just wanted to get you familiar with some of the units of measurement that you will encounter in the vibration test field. What is dB? Decibels is a unit of measurement which is a logarithmic relationship between two values. It calculates the change in level from a 0 dB arbitrary reference level. Now what does this mean? Well, this means that you can select any point on a graph and choose it as your 0 dB reference. Once you have a reference point, any change in that reference could either be an increase or a decrease in gain or in power level. So that is all a decibel is. It provides a logarithmic relationship between a reference and a change from that reference point. The power equation for calculating the change in level for acceleration in terms of vibration is 20 times log base 10 a1 over a0, where a0 is the input acceleration and a1 is the response of the input. Now let's go ahead and perform an example. Assuming 5G as your 0 dB reference, calculate the new G level when the gain is 6 dB. Now we're going to use the logarithm formula that we just saw in the previous slide, and afterward I'm going to give you a cheat sheet on finding your power factor for a given dB level. But first we're going to actually perform a problem using the logarithm formula so that you can understand and appreciate where these values come from. Now, if you have any questions on how I come up with the values or how I solve this problem, do a Google search on logarithms. I don't want to turn this into a math class, and you can find all the information you need online on how to solve a logarithmic problem. So let's go ahead and write down the formula that we just saw in the previous slide, which was 20 times log base 10 A1, which was the response of our input, over our response A naught. And this is equal to dB. Now this equation can be used to find your dB level if you know your response and you know your input. In this case, we don't know our response, our A1, but we do know our dB. So we are going to go ahead and plug in 5 for our A naught, that is our response or our input, and we know dB, which is 6. So let's go ahead and plug these values into the equation. We have 20 log base 10 A1 over 5, because 5 is our input, our A naught, is equal to 6. Okay, now we're going to go ahead and start simplifying this problem. First, we're going to divide both sides by 20. Okay. Now we are going to simplify the fraction 6/20ths into 3/10. And then we're going to simplify this even more and turn it into a decimal value, which is 0.3. Okay, and now we are going to use some logarithmic rules. Log 10 becomes 10, and 0.3 becomes the exponent of 10, and A1 over 5 will be moved over to the other side of the equation as A1 5. Oops. So 0.3 is the exponent of 10, because log base 10 becomes 10, is equal to A1 over 5, and this becomes, we're going to go ahead and multiply both sides by 5, so we have 5 times 10 with an exponent 0.3 is equal to A1. Now, 10 exponent 0.3 to the power 0.3 becomes a value that is 1.98, and there's some other numbers to it, but we're going to go ahead and round it up to 2. So this becomes 5 times 2 equals A1. Therefore, A1, our response, is equal to 10 Gs. So when you have a 5G input and a gain that is 6 dB, your response will be 10 Gs. So when you have a 6 dB level, it is estimated that you have a power factor of 2. Now let's go ahead and look at that table that I told you we would look at earlier before we perform this problem. Here is a table that relates our power factor or our gain or loss factor to a given dB value. Here you see our 6. In this case, it's plus 6.02. Like I said, at 6 dB, it becomes like 1.9888, and we round it up to 2, but So you have 6.02 dB2. So this is similar to the problem that we just solved. And then you have 12 with a power 12.04 with a power factor of 4. So you would, if you had a 12 dB increase from 5G, your input reference, you would have a 20G response. But as you can see, this table is a quick reference cheat sheet for finding what your power factor is and for finding what your response or your increase in acceleration is for your vibe test based on the dB value that you have. Okay, moving on. What is PSD? Power spectral density is the unit of measurement for random vibration testing. The unit of power spectral density is G squared per hertz. So gravitational squared per hertz. Hertz is the unit of measurement for frequency. Now we're going to go into more detail, and I'm going to define random vibration later in this presentation. But for now, once again, I wanted to get you familiar with some of the abbreviations you will use in the vibration test field. Now that we've gone over some of the major abbreviations of some of the units of measurement that you use in vibration testing, let's go ahead and define some terminology you will hear quite frequently in vibration testing. We will define displacement, we will define velocity, we will define acceleration, we will define what is vibration, we will define sine vibration, and we will define random vibration. What is displacement? Displacement, which is a vector quantity, just like gravitational force is a vector quantity, so it's expressed in both magnitude and direction, is a change in position of a structure with respect to time. Now let's look at displacement graphically. Here is a position which is represented by r on the vertical axis versus time, which is represented by t on the horizontal axis graph. Now, here you have a change in your position because you have an increase in your position, a positive increase in position. And here you have no change in position over time. Here is your increase in time. As time increases, from this point to this point, you have no change in position. And here you have a negative change in position back to the horizontal axis. And once again, you have no change in position. Now, displacement is a change in position with respect to time. So this slope here and this slope here represents that displacement is occurring. A change in position over time is occurring. Displacement is tangent to the slope of the horizontal graph. So when you have a change in position, you have displacement, which is tangent to the slope of the position graph versus time graph. And here I'm representing that displacement is tangent to the slope. Okay, well, let's look at this position graph now in terms of displacement. Let's actually plot displacement over time. Okay, here is the displacement, which we are going to call displacement x on our vertical axis versus time, which is represented by t, once again, on our horizontal axis. When we had that slope upward on our position graph, it was a linear slope, which means that our displacement was constant. And here you have a constant displacement representing that linear slope. And it is a positive displacement since we had a positive slope. Now, at the next point in time, we had a plateau on our position graph, which showed no change, positive or negative, in our position. So we had no displacement from this time point to this time point. And then we had a negative slope in our position graph. So we had a negative displacement from this time point to this time point. And once again, we had no change in position from this time onward, so we had no displacement. What is velocity? Velocity, which is a vector quantity, just like displacement and just like gravitational force, is a change in displacement with respect to time. Its unit of measurement is meters per second. Now let's look at velocity graphically. Here you have a displacement versus time graph. X on the vertical line represents your displacement, and t on your horizontal line, axis line, represents time. Here you have a slope which represents a time or change in displacement. When you have a change in displacement, you have velocity. Velocity is a change in displacement. And once again, just like displacement is on the position slope, velocity is tangent to the slope of the displacement graph. And once again, I will draw this to represent that velocity is tangent to the slope of the displacement. Okay, so when you look at this graph, here you have a positive slope on your displacement versus time graph, which means you have a positive velocity. You have a positive change in displacement, so you have a positive velocity. Then you have a plateau from this time point to this time point, which tells you that you have no change in displacement, which means you do not have velocity. Now, from this point to this point in time, you have a negative slope or a negative change in displacement. Therefore, you have a negative change in velocity. Now, let's go ahead and look at a velocity versus time graph. Here you have a velocity versus time graph. Velocity is represented by v on the vertical axis, and time is represented once again by t on the horizontal axis. From this point to this point in time, you have a constant velocity, since you have a linear slope on your displacement versus time graph. So a linear displacement means you have a constant velocity. From this point to this point, this was the plateau on the displacement versus time graph. You have no velocity. So no change in displacement means zero velocity. And from this time point to this time point, you had a negative change in displacement. Therefore, you had a negative velocity. And for the remainder of the time, you had no change in velocity, since you had no change in displacement, or you had no velocity since you had no change in displacement. What is acceleration? Acceleration, which is a vector quantity. Now don't get acceleration confused with gravitational acceleration. Gravitational acceleration is a scalar quantity, while acceleration is a vector quantity, which is expressed both in magnitude and direction. Okay, so acceleration, a vector quantity, is a change in velocity with respect to time. The unit of measurement for acceleration is meters per second squared. Okay, let's go ahead and look at acceleration graphically. Here we have a velocity versus time graph. Now, acceleration is tangent, just like velocity, and velocity is tangent to the slope of displacement, and displacement is tangent to the slope of the position graph. Acceleration is tangent to the slope of the velocity graph. Once again, I'm going to draw this out. But velocity is the change, or excuse me, acceleration is the change in velocity with respect to time. And here we see it is the slope, tangent to the slope of the velocities of the velocity graph. Okay, so we have from this point to this point a change in velocity, therefore we have acceleration. So when you're changing speed or you're changing velocity, you have acceleration. From this point to this point, we have a plateau on our velocity graph, which means we have no change in acceleration. Now, let me go back real quick. This is a positive slope, so it is a positive change of velocity, which means we have acceleration. When you have a negative slope in velocity or a negative change in speed, you have deacceleration. So from this point to this point, you have negative acceleration or deacceleration. Okay, let's look at acceleration graphically. Here you have an acceleration, which is represented by a on the vertical axis, versus time, which once again is represented by t on the horizontal axis graph. Okay, and we had a linear velocity slope in the previous slide, so we have a constant acceleration from this point to this point. Then you had a plateau on your velocity graph, so you had no acceleration from this time point to this time point. And then you had the negative slope, which meant you had a negative acceleration or deacceleration from this point to this point. And then from this point onward, you had no change in velocity, so you had no acceleration. Okay, moving on. What is vibration? Vibration is an oscillating energy which is the result of a force inputted into a structure or system which causes it to be displaced from its equilibrium or resting point. Now, vibration energy is based on frequency and on the amplitude, the intensity at which it causes a structure to move at a given frequency. Now, deformation shapes are dependent upon the frequency at which the vibration occurs at. And also, the size of the deformation at that shape is dependent upon the amplitude at which the force and frequency is being driven at. Now, this goes into when you start talking about deformation, you start going into modal analysis, which is a related but different field from vibration testing. It is more on the engineering side of structural testing, and we will go into more detail on modal analysis and modal testing in a later presentation, but right now we're just going into the basics of vibration testing and vibration terminology and application. But I wanted to get you familiar with some of these terms. And to get you a little more familiar with modal analysis, we're going to go ahead and look at a mode of a cantilever beam. Here is the third mode of a cantilever beam. The third mode is a vertical bending mode. Now, modal analysis is very important in determining how your structure or system will react at given frequencies and given amplitudes when vibration is inputted into your system or structure. Now, you'll be able to use this information to determine whether, along with collected field data from, let's say, a car engine, which inputs vibration into your component or structure on a car, or from a rocket engine, which inputs vibration into your system or component, which is mounted on your rocket, and you'll be able to take that data and compare it to the modes and be able to look at the frequencies at which your modes occur, and look at the frequencies and amplitudes of the vibration source, the force that's causing your vibration, which could be an engine or wind passing across a tower or building, and you'll be able to determine whether or not those modes are in the operating range of your system, and be able to determine whether or not your structure will be damaged as a result of the operational vibrations that it will be exposed to. This is important in design because you will need to know where your modes, where your resonant frequencies of your structures exist in order to design a system or structure which is outside, which has modes or resonant frequencies, if possible, outside of your operating vibration range in order to prevent stress to your system. Now, once again, we're going to go into more detail about this later on, but I wanted to get you familiar with modal analysis and modes and system or structural deformation. Here we have a spring mass system. Now, this spring and mass are oscillating at a single frequency. It oscillates at its natural frequency or resonant frequency, which for a spring mass system is dependent on the stiffness and the mass of the system. Now you see that the spring mass system oscillates at its given frequency and its given amplitude for an indefinite period of time. This does not occur in the real world because in the real world you have dampening. Dampening causes a structure or system to give up its energy in the form, vibration energy, in the form of friction, or in other words, heat. So in the real world, a structure or a system will move and eventually the energy will decay as it is converted into heat through friction. Now let's go ahead and calculate the natural or resonant frequency of this spring mass system. Now, we're not going to use any math. It's going to be actually except for division, it's going to be a very simple division problem. Now, I'm going to keep track of time, and I want you to keep track of cycles. Remember, frequency is cycles per second. So let's go ahead. You go ahead and start counting the cycles when I say go, and I will count the number of seconds. We're going to count to 10. So I'm going to count to 10 seconds. You count the number of cycles within that 10-second period. Okay, let's begin. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Stop. Now, if you counted correctly, you should have 10 cycles. Is that correct? Okay, well, you have 10 cycles. I have 10 seconds. Let's go ahead and divide 10 cycles divided by 10 seconds, which gives you a resonant or natural frequency of 1 hertz. So therefore, this spring mass system is moving at its natural frequency of 1 hertz, which also explains why there's so much displacement, because at lower frequencies you have higher displacement. Okay, let's go ahead and move on. What is sine vibration? Sine vibration is an oscillatory motion that occurs at individual frequencies. An example of a sine vibration test is a sine sweep. What is a sine sweep? A sine sweep is a sine vibration test that either sweeps up or down through a range of frequencies. It sweeps through one frequency point at a time. Okay, let's look at sine vibration graphically. Here is a sine vibration graph for a sine vibration test. Your vertical axis here is in G's, Gn, which is also G's, gravitational units. And your horizontal axis here is your frequency, which is expressed in hertz. Now this graph goes from 5 to 2000 hertz. Well, if you round this value up, it's 2000 hertz. And here is your profile, which for this test is a constant amplitude or constant G level at 0.5 Gs. Now, how a sine vibration test is performed is it either starts at your lowest frequency or your highest frequency, and it sweeps upward one frequency point at a time, or sweeps downward one frequency point at a time. Now, the sweep rate at which your test sweeps through the frequency range is called octaves per minute. Now, what is an octave? Well, in vibration testing, an octave is a doubling of frequencies. So, from 5 to 10 is 1 octave, from 10 to 20, 20 to 40, 40 to 80, and so forth. That is an octave. So, you would determine the number of minutes it takes to sweep through an octave will determine the amount of time it takes for you to make a complete sweep from your lowest frequency, 5, to your highest frequency, 2000 hertz. or from your highest frequency, 2000 hertz, down to your lowest frequency at 5 hertz. Now moving on, what is random vibration? Random vibration is a non-deterministic motion that is representative of most real-world vibrations. The attributes that make this type of motion random are phase and amplitude, which future actions cannot be predicted. Now, going back, I told you that you would appreciate the unit GRMS because RMS is expresses magnitude for a varying quantity. And now you see why it's used in random vibration testing. Because random vibration testing has content which varies randomly. So GRMS is the unit of measurement you would want to use to express the magnitude of a varying quantity. So now you understand why GRMS is used for random vibration testing. Okay, let's go ahead and look at this graph. Should look familiar to you. Here is a random vibration graph. Now, random vibration, unlike sine, does not occur at a single frequency at a time. It occurs at multiple frequency points simultaneously. And its amplitude and the phase of these vibration points at each frequency is random. Now, this is more representative of the real world. For instance, when you drive over a bumpy road, that is not sine vibration. That the vibration you're feeling is not sine vibration. It is random vibration. Now here you see a plus 3 dB per octave slope, and over here you see a negative 3 dB per octave slope. Now we kind of dabbled into octaves when I talked about sweep rate for a sine vibration test. Let's go ahead and define octave again. Octave is the doubling of frequencies. It is so for instance, one octave is from 20 to 40 hertz. That's one octave. And then 40 to 80 hertz is another octave. So each of these is one octave. So octaves for vibration testing are a doubling of frequencies. So this slope is the amplitude is increasing at 3 dB per octave. So the level of your amplitude, the intensity is increasing by 3 dB for every octave for this profile. And once again, here's your 6 GRMS. So the total acceleration content for this profile is 6 GRMS, which of course is the area under the curve of your spectral random line. Okay, let's go ahead and move on. Oh yeah, here, one more thing. And here, your vertical axis is described in power spectral density, which we had expressed earlier, is the unit of measurement used for random vibration testing. And here you have your horizontal curve, which is in frequency. Now, one more thing too is when you control a vibration test, you are controlling at only certain frequency points. You are not controlling at every single point, even though every single frequency point here is occurring in your random vibration test. You're only controlling to certain points. Now, the more points you are controlling to, the higher your resolution or the greater your control is. So lines of resolution is the number of control points number of frequency control points that you are controlling to for a random vibration test. Today we covered the abbreviations G's, G's peak, G's RMS, millivolts per G, picocoulombs per G, decibels, and power spectral density. We also defined displacement, velocity, acceleration, we defined vibration, we defined sine vibration, and we defined random vibration. Thanks again for watching this presentation. My name's Tom Resh. I'm an environmental test specialist, and if you have any questions or comments regarding the presentation you just watched, feel free to email me at tomvibetest@gmail.com. Now, I need to give credit to where I got some of the images that I used for this presentation. Under the definition for vibration slides, I used images from Wikipedia. Also, The spring mass system was also an image that I took from Wikipedia. And the screenshot for the sine vibration test profile was taken from a screenshot of the LDS Dactron laser software. Thank you again for watching and have a great day.